Food products are routinely screened for important organoleptic characteristics, such as smell, aroma, and color, as well as to guarantee that microbial content is below the maximum allowed threshold concentration. In the past, offline screening techniques were used, where a limited number of product samples were sent to a laboratory to be tested and the results became available with long delays. Today, automated production methods with integrated monitoring systems allow much faster response and the possibility to screen all the products with non-destructive measurements. Ice cream mixes are normally stored in dedicated machines maintaining the product at the target conservation temperature, normally in the range 2 to 6 Celsius degree, while pasteurization cycles are carried out at regular intervals of 1 or few days to lower the microbial concentration below the legally allowed threshold. Different types of mixes, however, require different machine parameters setting. To this purpose, in practice a distinction is made between milk and fruit-based ice creams, requiring different conservation temperatures and frequency of pasteurization cycles. Within the milk-based products a further, less decisive discrimination is that between creamy and frozen yogurt products. Electrical impedance spectroscopy is often used for electrical characterization of food products. The sample under test is placed in direct contact with electrodes and stimulated with a sinusoidal test voltage. The current through the electrodes due to the test signal is measured and the complex impedance can be calculated as shown in the figure. In electrical impedance spectroscopy, the sample is stimulated with a sine wave signal of fixed amplitude and a definite range of frequencies. Then, a suitable electrical circuit is used to model the system composed of the sample under test and the electrolyte. The measured impedance data are then fitted to the selected electrical circuit model and the corresponding electrical parameters are extracted. The electrochemical system composed of sample under test and electrodes is, however, a nonlinear system, and to effectively apply electrical impedance spectroscopy, generally the test signal features a small amplitude value so to confine the system in a pseudolinear region. Nevertheless, the study of the electrical response in the nonlinear region, using larger amplitude excitation potentials, can extend the knowledge and provide additional data on the tested sample. The objective of the study is to discriminate a set of 21 ice cream mixes, different for composition and producers, in two different groups, milk-based and fruit-based mixes, with eventually a second-level discrimination of the milk-based products and creamy mixes and frozen yogurts. To this purpose, the whole set of ice cream mixes has been subjected to the following tests. Electrical impedance spectroscopy measurements with a sinusoidal test signal of amplitude 100 mV in the frequency range 20 Hz to 10 kHz. The acquired spectra have been analyzed to validate the electrical model and the model parameters have been estimated. The electrical response in the nonlinear region has been studied by stimulating the sample with a sinusoidal test signal of frequency 20 Hz and amplitude in the range 10 mV to 2 volts. The measured data has been fitted to a nonlinear empirical model and the model parameters calculated by Liebenberg-Marquardt algorithm. pH measurements have been performed by means of a Krisen Mycroft 2000. The instrument has been calibrated before each measure using standard buffer solutions featuring pH 4 and 7 respectively. The setup used for the experiments is illustrated in the figure. The product samples are incubated in a thermal chamber providing the target temperature of 35 Celsius degree with an uncertainty of 0.1 Celsius degree. Electrical characteristics of the sample are measured with an LCR meter Agilent T4980A, controlled with USB interface by a PC system that is also used to acquire measured data and further data processing. The sample under test is placed in a 10 ml container with cap-shaped stainless steel electrodes. Two types of sensors are used. Sensor A consists of 2 electrodes while sensor B has 4 electrodes that are shorted together in couples as shown in the figure. The difference between the two sensors is related to the generated electric field. Sensor B is characterized by more homogeneous electric field with higher values than sensor A for both the field and its gradient. Measurements have been performed on a set of 21 ice cream mixes, different for ingredients and producers, which can be classified in two main categories, fruit and milk-based. The latter category can be further divided in creamy and frozen yogurt products. The ice cream mixes as well as the measured pH values are listed in the table. Those from 1 to 14 are milk-based. Creamy ones from 1 to 10 and frozen yogurt mixes from 11 to 14, while those from 15 to 21 are fruit-based. The discrimination of milk-based mixes and creamy mixes and frozen yogurts can be reliably achieved by pH measure since frozen yogurt mixes feature a significant lower pH value. The electrical model used to fit the data in the investigated frequency range is composed of a resistance, accounting for the resistance of both the sample and the interface, and a constant phase element, resulting from the essentially capacitive component due to the interface electrode medium. Since the ice cream is an unstructured material, no distinct dispersion exists within the radio frequency range up to several megahertz. The sample impedance is thus purely resistive while the reactive component is essentially due to the electrode interface. The electrical parameters are determined by best fitting the experimental data with the proposed electrical model for all ice cream mixes and both sensors. The determination coefficient between experimental and fitted data is found to be never lower than 0.998, thus validating the electrical model. Statistical analysis of the measured data indicates that significant differences exist between fruit-based and both creamy and frozen yogurt mixes in the case of the bulk resistance. Fruit-based mixes are generally characterized by higher values of the resistance than milk-based mixes. However, a small number of fruit-based mixes exhibit values of resistance comparable with those of the milk-based group, due to the presence of potassium salts that greatly enhances conductivity. Thus electrical impedance spectroscopy in the pseudo-linear region cannot reliably discriminate between milk-based and fruit-based ice cream mixes. The electrical characterization in the nonlinear region is investigated measuring the impedance modulus with a sinusoidal voltage signal of fixed frequency and amplitude in the range 10 mV to 2 volts. The results indicate that nonlinearity is stronger at lower frequencies. Thus, in the following, nonlinear characterization was carried out at a frequency of 20 Hz. In order to characterize the electrical response in the nonlinear region for the tested products, the curves have been fitted with the empirical model in figure, and the slope in the nonlinear region, lambda, has been calculated for all tested samples and both sensors. These results clearly indicate that measurements of lambda provides a reliable method to discriminate milk-based from fruit-based ice creams, with sensor B resulting in larger differences and thus more reliable discrimination. In conclusion, the feasibility to discriminate different groups of ice cream mixes has been shown. The basic discrimination between milk-based and fruit-based mixes is possible with the electrical characterization of the sample in the nonlinear region. A second-level discrimination of the first group between creamy mixes and frozen yogurt is possible measuring the sample pH.